Hello students. In this video we're going to learn a little bit about acids and bases. We're going to mostly cover the conceptual stuff in this video, and then I'll follow it up with a video about how to do pH calculations. But let's go through some of the content. We'll try to talk a little fast here because it's not a lot, but it can stretch out as I explain it. So let's hop right into it. First of all, when we think about acids and bases, you encounter these on a daily basis, and these have been around for a very long time, and people have known about them. And some common properties of acids that you may want to be familiar with. Number one, acids taste sour, and bases taste bitter. Now, this has evolved in humans since acids or bases or both could be poisonous. The human tongue evolved sort of a warning system to let you know that you're encountering acids and bases in nature. And so your taste buds, that sour taste you get, is actually a biological warning that, hey, this is an acid. Are you sure you want to eat this? Reevaluate it before you swallow it. And then for bases, that bitter taste is even more important. If you think about it, you probably like acid. You like sour flavor more than you like bitter. Most people just spit bitter stuff out. And that makes sense because in nature, bases are more poisonous typically, especially from plants, and those alkaloids are more bitter and more poisonous. And so when you bite into something that's bitter, you're like, nope, I got to get rid of this. Also, acids and bases interact uniquely with this natural compound, this thing called litmus. And we make litmus paper out of this natural compound now, or at least we dye the paper with litmus. When litmus comes into contact with an acid, it turns red, so it's an indicator. And then in the presence of a base, the litmus turns blue. And the magic behind that is simply the compound itself in litmus just changes its structure. It doesn't really break down as much, it just changes its structure a little bit and interacts with light a little bit differently. One final thing about bases is something you may have noticed in the shower. When you get a bar of soap wet, it's really slippery. Soap has one important component called lye, L-Y-E, that is sodium hydroxide. And so that slipperiness of the bar of soap is the sodium hydroxide, which is a base, that makes it feel very slippery. Now, chemically speaking, what is an acid or base? Well, they are polar, or in the case of some of the strong bases, ionic compounds, fully ionic. When you dissolve strong acids and strong bases in water, they're going to either dissociate fully if they're strong or react slightly with water through an acid-base reaction. That's just the weak stuff that does that. But importantly, all acids and bases have to be aqueous. They have to be in water to do what they want to do. At the bottom of the screen, you see just the classic acid-base reaction. This is with hydrochloric acid plus sodium hydroxide, and we can see that they do a double replacement swap where the sodium goes to the chloride to make common table salt, sodium chloride, and then the H and the OH go together to make water. So that is a very basic acid-base neutralization reaction. Before we get too much into this, let's talk about defining what an acid and base is. How could you look at it and know the difference? Well, the earliest definitions of acid and bases came from a Swede by the name of Arrhenius. He's the person who actually discovered and wrote the first paper outlining ions. And so Arrhenius noticed some things that acids had in common was the presence of H, the hydrogen in the formula. And then as an ion, there would be this hydronium, H positive, or more accurately, H3O positive. So a lot of his definition was about when you put the substance in water, what are we going to see? We're going to see more H, and that was what he defined an acid as. And then Arrhenius defined a base as a substance that had hydroxide in it, in the formula, so that when you dissolved it in water or put it in water, then the OH would come off the compound, become an ion, float around in the solution, and so increase the concentration, i.e. the molarity of the hydroxide ion. So Arrhenius' definition of acid and bases were just, hey, do you have H that can cause the molarity of H positive to go up, or do you have hydroxide which can cause the concentration of hydroxide up in solution? And that sounds very general, but really, in reality, this definition is very restrictive. It's the most restrictive of the definitions. So some time passes, and we get into the late 19th, early 20th century when we start trying to come up with a better definition, a more inclusive definition of acids and bases. So Bronsted and Lowry set out to define acids and bases not on kind of how they're constructed or what they have in them, but more like their behavior. How do acids and bases behave in a chemical reaction? So they said an acid is a proton donor. And now keep in mind, a proton is just the H positive ion. Hydrogen atom, if you use the most common isotope, protium, which is one proton, one electron with no neutrons, that's a very simple atom, one proton, one electron. So if you lose the electron to become a cation, the H positive is just really a proton floating around. And so an acid will give that proton, in other words, it will give the H to the base. And Bronsted-Lowry said a base then is a substance that will take that proton from the acid and thus become a proton acceptor. And then finally we have the Lewis definition that has come about in the 20th century. It's a much more inclusive definition. And now Lewis acids and bases really also kind of take us out of the requirement for aqueous, even though that makes it easier. But Lewis says acids are electron pair acceptors and bases are electron pair donors. For now, these are not in the scope of first year chemistry. If we do these, I'll make a separate video for the AP chemistry folks who might need that. But we're going to focus on Bronsted-Lowry. It is the most important definition of acids and bases for high school chemistry, especially AP chemistry. So, as I mentioned, it's not all inclusive. And to be a Bronsted base, you really have to have a non-bonding pair of electrons. So you draw the Lewis structure around the central atom, or I guess it doesn't have to be the central atom, but another atom in the Lewis structure. You have to have a pair of electrons that can take that H and form a bond with it. And because of this definition of donating and receiving protons, that means some substances can do both. They can be acids or bases, and we call those amphoteric. All right, so let's take a quick look at a Bronsted-Lowry reaction and how we can identify the acids and the bases. So in this first one, hydrochloric acid, and then we have water. So in this case, water is going to act as the base. We know hydrochloric acid is an acid, so here water will be a base. So let's look at what happens. I can see over here on the product side that the H2O has gained an H. Gained an H. It's accepted an H. So that means that water is the base. Where did it come from? Well, we can see over here that the HCl has become just chloride. So it gave the H to water. Water said thank you. It formed this, what we call hydronium. It's an ion, and left behind the chloride. So that is a Bronsted-Lowry acid-base reaction. It's not exactly double replacement like the one on the first slide, but it's still an acid-base reaction. Now down here at the bottom we have a base reaction. Here ammonia is a base, and now water will be an acid. So let's look at what happens here. Ammonia goes to ammonium, so it had to add an H, and that H came from the water. So water donated an H to ammonia to make ammonium and left behind the hydroxide from water. Now these products in acid-base reactions are what we call conjugates. And so a conjugate is, in this product side, they can go ahead and start reacting as well to reform the original reactants. This is especially important for weak acids and bases, which we won't do a lot of in this video. But in the reverse reaction, ammonium will react with hydroxide. Ammonium will now give the H back to hydroxide, and that will reform ammonia and water. So in the reactants, ammonia is a base. On this side, ammonium is a product that will now become an acid as it reacts with the other products. Ammonia and ammonium form what we call a conjugate acid-base pair. Again, this only happens because acid-base reactions can sometimes go backwards and forwards. So let's just take a quick moment to take a look at some practice with that. And get all my buttons lined up here. There we go. So let's do some quick practice here with conjugates. I'm not going to do this whole worksheet, but I thought it would be good just to practice a few. So in this number 1 here, I've given you 5 acids. So let's figure out the conjugate base for these 5 acids. Remember what an acid does. Acids donate H positive. In other words, they give it away. So really all we have to do is remove an H positive from each of these acids. So if I take away an H, that's going to leave behind an NH2. And remember, I'm taking away an H positive, so I also have to remove a charge, and that will leave behind NH2 minus. Okay, the next one with this hydronium. Let's remove an H positive, so that goes back to water, and the +1 charge goes back to 0. So that's just water. And we'll stop on C here with this part. This is called bisulfite or hydrogen sulfite. So let's donate a hydrogen that will leave behind SO3, and we have to take away a positive charge again, so that's going to be -2. So if you need to, hit pause and think about that and see and make sure that you can actually see the pattern. Do D and E, and I'm just going to throw the answers up real quick. All right, so that's finding the conjugate base. In number 2, we're going to do the opposite. We're going to take some bases and we're going to find the conjugate acids. So a base, remember, adds or accepts the H positive. So as I go from base to acid here, conjugate acid, I need to add an H to it. So we'll put an H in front. Now that adds a positive charge. So this is going to become -2 instead of -3. For ammonia here, we're going to add an H positive. So it becomes NH4 with that positive charge, from 0 to positive charge. Okay, and then for C here, we have bicarbonate. So it wants to accept a proton. It's a base, it's going to accept. So we need to add another H. So H2, CO3, and -1 goes up to 0. We add a charge. All right, try D on your own. Hit pause if you need to. And if we add that one, we get CH3, OH2 positive. All right, real quickly here, number 3. Let's just do the reactions and then we'll get back to the main slide show. So here we have phosphoric acid and ammonia. So when you look at this, I hope you can identify the acid and the base. That H in the front is a dead giveaway for the acid, which must mean ammonia here is the base. So now let's do the Bronsted-Lowry work here. The acid is going to donate a proton, so we're going to give NH3 a proton, and that'll make NH4 positive. Okay, it still will be aqueous. And now what did that leave behind? Phosphoric acid donated, so its conjugate will be H2PO4, this time with a minus charge. So we've created these two products, and now if we just covered those up and looked at how these would behave, this ammonia would give an H back to this one, so this is the conjugate acid. and this is the conjugate base. And they form what we call conjugate pairs. I call them before and afters. All right, hit pause and try 3B if you want to, and I'll just throw the answer up so you can check your work. All right, so carbonate's the base, sulfuric acid's the acid, so that must mean this is the conjugate acid and this is the conjugate base. All right, hopefully that helps you a little bit with conjugates. Let's get back to the PowerPoint here. While I'm turning it on, let me remind you that if you do have questions about it, please make sure that you ask your teacher and to go over it with you. All righty. Now, acid-base reactions, we've done some Bronsted-Lowry stuff here, but some of them are even more simple than that. These would be more of your Arrhenius type things. We don't want to forget about the easy stuff. So acid-base reactions are often called neutralization reactions. That's the third bullet on the screen right now. And these are basically double replacement reactions like you learned in pre-AP chemistry. And so if you see from the diagram there, you have AB plus CD, so that would be H, and then A would be like the H ion, B would be your anion, and then for CD that's a base where C would be the cation and D would be the anion. And so they just do a partner swap. And the products of this double replacement Arrhenius acid-base reaction is always the same thing, the same general products. Water, which you get from the H and OH connection, and then the other product is what we call a salt. Not always the salt, but a salt, which just means an ionic compound. So that is called an acid-base neutralization reaction. So let's go back to the .chem and do a couple of easy neutralization reactions. Of course, I say it's easy. Flipping back and forth between cameras is not easy. But we're going to get it done. All right. Again, we're just going to do a few of these. So this very first one, we have HI plus NaOH. And everything is aqueous. And so what we're going to do is we're going to do a double swap. The acid is cation anion, and the base is cation anion. So H is going to come over here, swap partners, and that with OH, and then we'll make water. And then Na and I will come in and form a partnership with NaI. So that's a double replacement swap. If we do just maybe one more here, carbonic acid plus strontium hydroxide. So again, we have an acid, we have a base. The cation here, H, is going to come over here, bond with OH, which is just water. And then strontium, keep in mind here that strontium is +2. It comes over here with carbonate, and keep in mind carbonate is -2. So they're going to form SrCO3, which will be a solid, I believe. So we get both a precipitation and an acid-base neutralization reaction happening at the same time. Now this one we do need to balance. You see we don't have nearly enough hydrogens and oxygens, so I need to put a 2 in front of that one. And you occasionally have to balance an acid-base reaction. So that's a neutralization reaction. I don't think you'll find that really difficult, especially if you learned how to do double replacement reactions during that unit. Okay, so we're almost through with this particular video. So let's just talk about the strengths of acids and bases. You'll hear the words strong acids and weak acids a lot, strong bases and weak bases. So when we use those terms, we're not talking about how reactive the acid is, believe it or not. or how corrosive it is. That's what it seems like it should be, but that's not really what it is. When we talk about strong acids, we're talking about the acids dissociating. Go back to that solutions unit, that vocab word, dissociation, breaking apart of the ions. Strong acids and bases dissociate 100%. They're highly soluble, and every molecule breaks apart into its ions. 100%, every one. Now, a weak acid or base will be slightly soluble in water, but it will not dissociate 100%. In fact, weak acids and bases typically dissociate less than 10%, and many of them are less than 5, less than 3% really. Very, very small degrees of dissociation for some of the weak stuff. So some strong acids you should probably memorize. These 7, the big 7, memorize them as strong, and then everything else is weak in terms of acids. So those are your 3 of your binary acids: hydrochloric, hydrobromic, hydroiodic. You'll notice that HF is not on that list. HF is a real nasty acid, but it's not strong by the definition of dissociation. And then we have nitric, sulfuric, chloric, and perchloric. In AP, we'll go into some discussions about why these are strong, but for now, just say, if you notice, those are some of your most electronegative anions. That helps make them strong, and the H is more easily lost. All right, so we're not going to talk about weak acids. Just know that if it's not strong, it's weak, which means it just doesn't dissociate 100%. All right, let's stop this video there at this point, and then we'll start a new video with how to do pH. So if you have any questions about acid-base definitions, make sure that you ask your teacher.